Hello everyone, welcome back. Now let's see what is normal distribution and how the shape of normal distribution looks like, some of its important characteristics, and also we will see some of the practical examples of normal distribution. So let's first start off with the definition of normal distribution. So it is a type of continuous probability distribution in which most data points cluster towards the middle of the range, and when you move towards the extreme it tapers off symmetrically. So that's the definition of normal distribution. If I show you the shape, or if I show you the diagram of a normal distribution, it will be much more clear. So let me draw it for you. So this is the shape of a normal distribution curve, and it is also often known as bell-shaped curve because it actually looks like a bell. So yeah, you can see here the most of the data points that we have is centered around mean, and on the extreme ends we have very less data. So that is what the definition says. And a normal distribution is defined by mainly two parameters, which is mean and standard deviation. So if you want to say that a variable x is normally distributed, you can say it using this particular expression. So here you what essentially you are saying is a variable x is normally distributed with mean as mu and standard deviation as small sigma. So that's how you can represent normally distributed data. Now, how mean and standard deviation affects the shape of your normal distribution, we will see that. Let me show you with a diagram. Here you can see two graphs or two plots or two distributions. So both are normally distributed, and the first one has its mean around 30 and it has a standard deviation of 1, whereas the second data has its mean at 50 and it has a standard deviation of 3. So I have plotted them in the notebook section, so you will be able to see it there. So you can see when the standard deviation is more, your plot looks more spread out, and that's what we actually learned in our lectures when we were talking about standard deviation. And here you can see that standard deviation is less, so the plot is much more narrowed and it has a bigger height as compared to our orange one. So when you shift the mean, so here we have a mean at 30, here we have a mean at 50, your plot shifts, and when you increase or decrease standard deviation, it will increase or decrease the thickness of normal distribution. Now you might ask why. So the reason is always area under the curve for normal distribution, it will be 1 because it's a density plot and we always have it as 1. So when you will stretch your curve on either of the sides, it will obviously reduce the height of your curve. So this would have given you a good understanding about how mean and standard deviation affects the shape of your normal distribution. Now let's see what is 68, 95 and 99.7 rule, which is actually very important. For that, let me draw a normal distribution again. Let's say our mean is here, and this is our first standard deviation, second standard deviation, and third standard deviation. This side, negative of first standard deviation, negative of second standard deviation, and negative of third standard deviation. Let me also write it. So the 68, 95, 99.7 rule states that 68% of your data lies between -1 to 1 standard deviation, -95% of your data lies between -2 standard deviation to 2 standard deviation, and 99.7% of the data lies between 3 standard deviation. So that's what this rule suggests, and it becomes very important when we will see central limit theorem, and we will also see its applications. Now let me show you some of the practical examples of normal distribution. World's population, height and weight is normally distributed. So if you see, most of the people will be around the average or mean of the height, and there will be very few people who will be very short, and there will be very few people who will be very tall. Same goes for weight as well. If you take an example of marks achieved by students, most of the people score around average. There will be very few people who will score like full marks, or there will be very few people who will score very less, or they will fail. So that is again normally distributed. Players retirement age, some of the players, because of injury or their poor performance, they have to retire early. Some of the players who are really very fit, so they go really long into their career. Most of the players retire at a usual age, so this again can be normally distributed. As for blood pressure, again, most of the people have average blood pressure of around 80, but then there are few people who will have very low blood pressure, and there will be people who will have high blood pressure problems. So again, this is also normally distributed. Now you can maybe ask two questions. The first question could be, why only till 3 standard deviation? And the second question could be, what if I don't want to just find how much data is between first standard deviation or second standard deviation? What if I want to find something at an arbitrary point, let's say from this point to this point? So this could be your second question. Now let me first answer the first question. You don't really have to just stick yourself till 3 standard deviation. You can go till 4, 5, 6, 7 infinity, because this tail never touches x-axis. It keeps going on, it keeps coming closer to it, but it never touches x-axis. So that's there. But usually what happens is, whenever a data point lies beyond 3 standard deviation, we take it as an outlier, because you saw that 99.7% of the data lies between 3 standard deviations. So that is the reason. Now as for second question is, if you want to find data point lying between arbitrary point, that's where z value comes into picture, and that is what we will look into in the next lecture. So that lecture should give you a good idea about how to find data point or percentage of data point lying between arbitrary points. Now let me take you to the notebook and show you how you can actually find these things. So here I'm generating two data, 10,000 data points each, and the first one has mean of 30 and 1 standard deviation, and the second data has mean as 50 and the standard deviation is 3. So again, you can see this, I have shown you this plot in the slides, but you can again see that standard deviation 3 has a wider curve, whereas the standard deviation of 1 has thinner curve, and their mean shifts the curve on this particular axis. Now I also wanted to show the actual example of how much data lies between first, second and third standard deviation. So here you can see the plot. So here I have generated data which represents the height of women. So you can see this is example which I have taken from previous videos. So I have generated 10,000 data points with mean as 160 and standard deviation at 5. And here I am plotting the distribution and also a few set of lines. So blue line represents our first standard deviation, red line represents second standard deviation, green line represents third standard deviation. And now I have also calculated how much data is lying between these lines. So in our first standard deviation, you can see here we have around 68.2% data points. In second standard deviation, we have 95.5 data points, and in our third standard deviation, we have 99.7% data points. So yeah, this also proves the 68, 95, 99.7 rule, and it will become even more practical when we will look at central limit theorem. But yeah, this is what I wanted to show. As for task, there isn't much that you can do. Probably what you can do is you can change sample size and see whether these values or these percentage stays the same. So you can try playing around and see that. So yeah, this is what I wanted to discuss in this video. Hope to see you in the next one. Happy learning.